The objective today is to explain how to create an OR gate out of transistors. So we're going to add more information to our transistor knowledge with a few Think Right shares today, and then we'll actually create one. I want to introduce the concept of field-emitting transistors, but not go too deep into that until we have a solid grasp of designing and reading schematics. What we've not started is creating what's called a full adder. That is a collection of transistors that is used to allow the computer to add. The day we get that done might be one of those huge aha moments for you in understanding how computers take binary numbers and turn it into stuff. Currently in progress is transistor placement for logic gates, and completed is your knowledge of the definition of a transistor and how this is one of the most significant things created by humans. Without the transistor, we have no computer or smartphone or gaming consoles. So far, we've been talking about and using a special type of transistor called BJT, stands for bipolar junction transistor. But there are other types out there. One of the types I mentioned in the agenda today is the FET, so more commonly used in high power consumption devices. And then the MOS, which stands for metal oxide semiconductor. And the MOS is a voltage controlled component. So I encourage you to experiment with this at the end of the lesson. However, through this discussion of MOS transistors, I just want you to understand a little about electricity and how electricity works. So there's two types of MOS transistors, the N-type and the P-type. When the gate has positive voltage, that closes the switch. When the gate has zero voltage, the switch is open. So what did I just say a MOS is? Don't worry about understanding this diagram to the lower right quite yet. Let's just break each one down. So complementary MOS uses both N-type and P-type transistors. The P-type is attached to the positive voltage, or to the positive side of the voltage. What this does is it pulls output voltage when the input is zero. And in your notes here, you're going to want to write down the P-type transistor is attached to what? Alright, and then quickly here, the N-type is attached to the ground, and it pulls output voltage down when the input is 1. Remember input, output, and truth tables? So when the input is a binary 1, right, that pulls output voltage down. So for all inputs, make sure that output is either connected to the ground or to the voltage, but not both. For your Think Right share here, what is the difference between P and N-type transistors? And now if you look at this diagram, I think this one does the best job at describing what I just tried to do through words. So the N-type transistor here, you see the base is here, and so the voltage is running in this direction because you can see the arrow right there. Think of the N-type transistor in terms of never points in. And then the P transistor, P-type here, has the voltage going the opposite direction, so it starts from the emitter. And a nifty way to remember this is it points in permanently. And now in your mind, think about how we've made these transistors into microscopic things. Microprocessors contain millions of these. The Intel Pentium 2 has 7 million. The compact Alpha has 15 million. And the Intel Pentium 3 has 28 million. On your typical motherboard, when you pull that out of a computer, it's going to be the transistor is just too small for you to see. And even for hobbyists who like to mess around with electronics, and they will get a transistor that looks kind of like this, just a big rectangle, it's actually not one transistor. There's many transistors inside of here. And what you do is you'll read a schematic or read directions as to what pin to connect to in order to create the thing that you want to create. So if we just look at the top left right here, you have pin number 1, pin number 2, and these are the input pins. So using binary, right, 0 or 1 will go here, 0 or 1 will go here, meaning either the electricity is on or it is off. And then you'll have some sort of output, and you'll connect to pin 3 to get that output. And I should clarify, when I say the electricity is either there or not, I'm not even completely telling the truth there. What a 0 is to a computer is anything that has 0 to 0.5 of a volt. So if there's a tiny bit of electricity there, it's totally fine. And then to make it a 1, typically a transistor will need either 2.4 to 2.9 volts to register as a 1. So later in this unit, we'll talk about a 2-bit decoder. It's pretty simple. But for now, the assignment of voltage ranges depends on the electrical properties of the transistors being used. So if you're in chemistry class, this is a good connection for you. Typical values for a 1, like I had said on this slide before, is either 5 volts, 3.3 volts, or 2.9 volts. It depends, okay? And then from now on, in our minds, if we just go with the 2.9 volt number, that would be a good one. So just try to think in those terms. And a quick slide showing you the different schematics for the different types of transistors out there. And every transistor will have these 3 components: a base, an emitter, and a collector. And no, this isn't quite a trick question. I just want to put all of our lesson together right here with this image. And at this point, you should be feeling pretty proud of yourself for being able to read some electrical schematics. In the bin eater video that I highly recommend you watch, he wires up an OR gate right here. So that's basically what he did. If you need more information, go ahead and search for making logic gates from transistors. You can watch his video from that title. Our focus today is on the OR gate, but let's do a quick refresh for some of the other types of gates out there. You got the NOT gate, which places the output higher up on the electrode, so this is where the output is coming from. Typically, you'll see the output down here for the other gates. For this NOT gate, how many transistors are being used? That was a pretty softball, easy question. What about the OR gate? How many transistors and inputs do you need for this OR gate? Alright, and at the beginning of the video I talked about us thinking about a full adder and how a computer can add and subtract numbers, binary numbers that is. So looking at something as complex as this, how many gates and inputs do you need? And I'll help you out with this because it might get a little tricky. Don't think of each of these as a transistor, right? Because they're not. It takes 1 transistor to make a NOT gate. It takes 2 to make an OR gate. So to answer this question, how many gates? Well, that's easy. There's 4 right here. You can easily see them. And then how many inputs? Well, we just have A and B. And if at this moment you're getting a little frustrated or thinking about why do I need to understand these things, these low-level things, well, here's a quote from Thomas Jefferson: "I like the dreams of the future better than the history of the past." I think that kind of wraps my thoughts around all the passion and energy I put into learning this low-level stuff. There's so many things yet to be created in technology that you'll need a good understanding of this, a good understanding of transistors and binary in order to build on top of that. One of my favorite things to do in class is pseudocode here. So this may seem a little silly at first, but it can be very helpful, especially when working on big projects. And all the programming languages I know of uses Boolean-like scenarios here. So when we're coding, it's like we are telling the computer how to handle binary by using binary-like or Boolean-like situations. So you might see something like this in coding. While a condition is occurring, then the computer is going to do something. So here's a better explanation. Think in terms of yourself. Like, while I am hungry, I need to eat. Like, I know to do that. You can also use the word if for Boolean logic. So if a student raises their hand, I call on them. Else, I should ignore them. If you want to get away from the pseudocode here, and pseudo meaning fake, being a prefix for the word fake, we can look at something like this that could appear in a typical JavaScript program. So maybe you establish that you're going to have an integer, and you're going to call this variable 5 right here. And so in order to test whether 5 is greater than 10, you can put these parameters inside of an if statement and then have something happen. If this number changes from 5 to something else, which either the programmer or the user can make happen, then there may be another result that occurs. And then bring this back to the pseudocode we were talking about. So if something happens, do this or else do that. Think of a pseudocode in video games. So if my opponent is in front of me and I press X, then punches them, or else stand there doing nothing. That's pseudocode for video game logic, but I think you're getting the point here that the computer sure can follow directions as long as you're just explicit about those directions. So think right share here, it's your turn to at least make one pseudocode example. You can do it with anything your imagination gives you. Maybe even use a website related example. And as long as you have the words if and then some sort of condition, you'll be able to get this think right share correct. And I really like talking about these types of expressions because it brings coding down to the binary level and connects them. And that was it for this lesson. I have a quick review scenario here to challenge you. So those who are really enjoying the electrical schematic stuff. But besides that, we're pretty much done here. So pick an IB question to answer. Pick one of the 7, and then here's the DOL. So the first one, these gates are being used when people use computers. This is true for when you are browsing on the web. Think of an example where Boolean statements could be used while browsing a website. Then write the pseudocode for it. So this is very specific to website browsing. And then I want you to describe or explain the purpose of Boolean logic. And bonus points if you could find a way to get the word LED as in light emitting diode or the word pixel into your explanation. But Boolean logic is the basis of all things computer. And of course, pseudocode is a nice little bridge to get from the Boolean logic to the understanding of how programmers work. And one last extra piece of information. If you're wiring up the OR gate inside of Tinkercad. Basically, here's your cheat sheet, or at least this is how I wired one up and made sure it worked.